The first week of January 1945. A requisitioned industrial warehouse on Berlin's outskirts, now serving as an examination facility for captured enemy ordnance. Dr. Hinrich Becker, chief weapons engineer at Kummersdorf Proving Ground, Germany's primary ballistics testing center since 1875, stood before a metal examination table. 3 American 105mm artillery shells lay before him, recovered from snow-covered positions near Bastogne, Belgium, during the Ardennes offensive. These shells appeared unremarkable at first inspection. Standard M1 high-explosive projectiles, the type that had been impacting German defensive positions across Western Europe since the Normandy landings 7 months earlier. The rifling marks on their copper driving bands confirmed they had been fired from M101 howitzers, the American standard divisional artillery piece. But these 3 shells had failed to detonate, and the field reports accompanying them from frontline units described something unprecedented. Soldiers from multiple Wehrmacht divisions, the 12th SS Panzer, the 26th Volksgrenadier, the Panzer Lehr, all reported the same phenomenon during the Battle of the Bulge. American artillery shells were detonating in midair with remarkable consistency, perhaps 20 to 30 meters above ground level. This created an airburst effect that rained fragmentation down into foxholes, trenches, and any ground-level defensive position. Traditional cover provided no protection. Casualties in targeted areas exceeded anything experienced from conventional artillery by a factor of 3 to 5, according to preliminary casualty reports compiled by divisional medical officers. If you appreciate evidence-based World War II history presented without dramatization, please like this video and subscribe to the channel. Leave a comment telling us where you're watching from. We have viewers in 47 countries now. Hairburst artillery was not a new concept in 1945. Timed fuses had existed since the American Civil War, but achieving consistent airburst required extensive calculation by experienced gun crews. They needed accurate range to target, precise meteorological data, including temperature and barometric pressure, and detailed knowledge of their specific gun's ballistic characteristics. Even with all this information, achieving a proper airburst high enough to avoid ground detonation, low enough to be effective, remained difficult. Achieving it consistently in combat conditions with moving targets, in winter weather with poor visibility, was considered nearly impossible by artillery doctrine of that era. Yet American artillery batteries were apparently achieving it every single time. The reports indicated no duds, no premature detonations, no shells impacting the ground unexploded. Every round functioned as intended. This level of consistency suggested something beyond conventional timed fuses. Becker had been ordered by Waffenamt, the German Army Weapons Agency, to determine how the Americans were accomplishing this. He approached the task with the methodical precision that had characterized his 15-year career in ordnance engineering. He photographed each shell from multiple angles using a Leica camera, documenting their external condition. He measured and recorded their dimensions. He examined the driving bands under magnification to confirm they matched American 105mm specifications from captured technical manuals. Only then did he begin the disassembly process. Artillery shells, even unexploded ones, remained dangerous. The main bursting charge, typically composition B, a mixture of RDX and TNT, could still be detonated by shock or heat. Becker worked slowly, using specialized tools designed for ordnance disposal. His assistant, Hermann Franke, stood ready with safety equipment, though both men understood that if something went catastrophically wrong, safety equipment would be irrelevant. Becker removed the nose cone of the first shell, exposing the fuse assembly. He stopped immediately. For perhaps 30 seconds, he simply stared at what the shell contained, not believing what his technical training told him he was seeing. The fuse cavity contained what appeared to be a complete miniature radio set. Becker could identify a transmitter circuit, a receiver circuit, an amplification stage, a battery assembly, and a triggering mechanism connected to the main explosive charge. The components were precisely machined and fitted together with extraordinary density. Nothing was wasted. Every cubic centimeter of available space had been utilized. Becker called Franke over. His assistant had worked as an electrical engineer for Telefunken, one of Germany's premier electronics firms, before being conscripted into ordnance services. Franke examined the device for several minutes before speaking. According to post-war interviews, his first words were, "This should not exist. These components cannot survive being fired from artillery." The technical objection was sound. When a 105mm shell is fired, it experiences acceleration forces exceeding 20,000 times Earth's gravity. This acceleration occurs over roughly 3 meters of barrel length, meaning the shell goes from stationary to over 490 meters per second in approximately 1/100th of a second. Any components inside the shell experience tremendous mechanical stress. Radio equipment in 1945 was inherently delicate. Vacuum tubes, the amplification devices that made radios function, were glass envelopes containing metal filaments and electrodes in a vacuum. They were fragile under normal handling. The idea of making them survive artillery launch seemed impossible to German engineers, whose own vacuum tubes required careful packaging even for ground-based transport. Yet the evidence before them indicated that American engineers had solved this problem. The rifling marks on the shell casing proved it had been fired. The radio components were intact, showing no signs of shattering or displacement. Somehow, these delicate electronic parts had survived forces that should have destroyed them. Over the following 8 hours, Becker's team completely documented the first fuse. They photographed every component. They made detailed sketches. They carefully removed parts for microscopic examination and chemical analysis. The vacuum tubes were smaller than anything in German production, roughly half the diameter of comparable German tubes. The glass was thicker, providing structural strength. The internal elements were more robustly constructed. Every design choice prioritized durability. The battery system was equally remarkable. It used a glass vial containing liquid electrolyte. The vial was designed to shatter during launch, allowing the electrolyte to mix with the battery's chemical components, activating the power source. This meant the battery could be stored indefinitely without degradation, only becoming active when the shell was fired. German engineers had theorized about such activation mechanisms, but implementing them required precision glasswork and carefully formulated electrolytes. The German manufacturing capacity, by 1945, could no longer reliably produce. The fuse operated on a straightforward principle. The transmitter generated radio waves at approximately 180 megahertz. These waves radiated outward from a small antenna that deployed after the shell left the gun barrel. When the shell approached a reflecting surface, the ground, a building, a vehicle, the radio waves bounced back. The receiver detected these reflected waves. As the shell got closer to the surface, the reflected signal strength increased. When signal strength reached a predetermined threshold, the trigger circuit fired the detonator, initiating the main explosive charge. The result was an automatic airburst at optimal altitude, typically 20 to 30 meters above ground. No calculations required, no timing settings needed. The shell determined its own detonation point based on proximity to the target area. Becker assembled his senior engineering staff 3 days after completing the initial examination. Present were Dr. Wilhelm Schäfer, who specialized in electronics and had worked on German radar development, Major Ernst Hoffmann, responsible for fuse production at several German manufacturing facilities, and 3 other engineers with expertise in metallurgy, precision manufacturing, and chemical engineering. Becker presented his findings and then asked the question that would define the meeting: could Germany replicate this device? The discussion that followed was documented in notes that survived the war and are now held in the US National Archives. The consensus was unambiguous. Germany could not manufacture this fuse with available resources and industrial capacity as of January 1945. Schäfer addressed the vacuum tube problem first. German vacuum tubes in 1945 were relatively large. The smallest tubes in production, miniature tubes used in portable radios, were still significantly larger than the American tubes in the proximity fuse. Creating tubes small enough to fit in an artillery shell, while maintaining functionality and surviving launch forces, would require manufacturing capabilities Germany no longer possessed. The precision glass working, the metal forming for internal elements, the quality control to ensure reliability, all exceeded what German factories could produce under wartime conditions. German industrial facilities had been under sustained Allied bombing since 1942. The Ruhr industrial region, center of German steel production, had been systematically targeted. By 1945, German factories were dispersed, operating with damaged equipment, supplied by a deteriorating transportation network, and staffed increasingly by forced labor with minimal technical training. Precision manufacturing, which requires consistency and quality control, had become nearly impossible. Major Hoffmann provided production data. German fuse manufacturing in 1944 had produced approximately 120 million fuses total for all types of artillery, mortar, and aerial bombs. These were predominantly simple mechanical fuses, timed fuses using clockwork mechanisms, or impact fuses using inertial triggers. Even these simple devices were experiencing quality control problems. Dud rates for German artillery ammunition had increased from roughly 2% in 1942 to nearly 8% by late 1944, indicating declining manufacturing standards. The American proximity fuse was orders of magnitude more complex than any German fuse in production. Each one contained components requiring precision to tolerances of hundredths of a millimeter. Each one required vacuum tubes manufactured to exacting specifications. Each one required careful assembly by trained workers, and according to intelligence estimates, the Americans were producing these devices in massive quantities. This led to Becker's second question. How many proximity fuses had the Americans manufactured? The answer came from multiple intelligence sources. Frontline reports indicated that American artillery was using proximity fuses as standard ammunition, not as rare, specialized rounds. Captured American supply documents suggested monthly shipments of proximity fuses to European theater exceeded 1 million units. British intelligence, shared through remaining cooperation channels, indicated that Royal Navy ships and British anti-aircraft batteries were also receiving American proximity fuses in large quantities. The team calculated that American production likely exceeded 40,000 proximity fuses per day by late 1944. This was based on observed usage rates, captured supply manifests, and estimates of American artillery ammunition expenditure during major operations. To place this figure in context, Germany's entire electronics industry in 1944 could not have produced 40,000 radio receivers per day, much less ruggedized miniature radio sets designed to survive artillery launch. American industry was manufacturing in one day what would take German industry more than a month, and doing so while simultaneously producing aircraft, ships, tanks, trucks, and conventional ammunition in quantities that exceeded Germany's capacity by even wider margins. Becker requested access to broader intelligence data on American war production. This was granted reluctantly by Oberkommando der Wehrmacht, the German Armed Forces High Command. Becker received files containing production estimates, economic analysis, and captured American documents that had been translated and assessed by intelligence officers. What Becker read confirmed his worst suspicions and exceeded them. The proximity fuse program, codenamed VT for variable time, had been developed at Johns Hopkins University's Applied Physics Laboratory in Maryland. Declassified American documents from post-war archives indicate the program had begun in 1940, accelerated dramatically after Pearl Harbor, and had involved over 800 scientists and engineers at its peak. But the development program, impressive as it was, paled beside the production program. American industry had converted multiple facilities to proximity fuse manufacture. Western Electric, the manufacturing arm of the Bell telephone system, had modified production lines originally designed for telephone equipment. Eastman Kodak had converted photographic equipment manufacturing to precision component production. Multiple other contractors contributed specialized parts. German intelligence estimates, later confirmed by declassified American production records, indicated the following manufacturing rates for proximity fuses. 1943, approximately 500,000 units total. 1944, approximately 12 million units. 1945 projection, over 10 million units in the first half of the year alone. The final production total, according to post-war American records, exceeded 22 million proximity fuses manufactured between 1942 and 1945. Becker pulled German production data for comparison. In 1944, Germany had manufactured approximately 40,000 aircraft of all types: fighters, bombers, transports, trainers. The Americans were producing more proximity fuses than that every single day. And these were not simple devices. Each proximity fuse was more complex than most radio receivers, containing more precision components than many aircraft instruments. The intelligence files contained other disturbing data. American aircraft production in 1944 had reached 96,369 units, according to captured statistical summaries. This was more than double Germany's production, but the raw numbers understated the disparity. American aircraft were on average significantly larger and more complex than German aircraft. A B-17 Flying Fortress heavy bomber required approximately 4 times the aluminum and 5 times the man-hours to manufacture compared to a Bf-109 fighter. American bomber production alone consumed more industrial capacity than Germany's entire aircraft industry. Ship production showed even more dramatic disparities. The United States had built over 5,000 merchant ships during the war using standardized production methods, the Liberty ships and Victory ships. Some Liberty ships had been constructed in under 5 days from keel laying to launch. Germany's entire merchant marine at the war's beginning had numbered roughly 4,500 ships, accumulated over decades. The Americans had built more ships in 3 years than Germany had owned at the war's start. Military vehicle production followed the same pattern. American industry manufactured approximately 2.4 million trucks during the war years. Germany produced roughly 350,000. The American truck production alone, setting aside tanks, jeeps, and other vehicles, exceeded German production by nearly 7 to 1. A supplementary section of Becker's report dealt with tactical impact, based on interviews with frontline commanders who had faced the proximity fuse during the Ardennes offensive. One interview, conducted with a colonel commanding an artillery regiment, provided detailed testimony about the weapon's battlefield effects. The colonel, his name was redacted in surviving documents, but he commanded elements of a Volksgrenadier division at Bastogne, described losing an entire battalion to proximity fuse bombardment in approximately 15 minutes. The battalion had been positioned in prepared defensive works, foxholes, trenches, and dugouts that would normally provide protection against conventional artillery. When American counter-battery fire began, the shells detonated 20 to 30 meters above the ground. Fragmentation from this altitude struck into every foxhole and trench. Men who would have survived conventional artillery fire, which typically produces fragmentation at ground level that passes over foxholes, were killed by fragments coming down from above. The battalion lost approximately 400 men killed or seriously wounded in that one bombardment. Normal casualty expectations from similar artillery fire using conventional fuses would have been 80 to 120 casualties. The proximity fuse had increased casualties by a factor of 4 in this instance. The colonel noted that after soldiers experienced proximity fuse bombardment once, their morale deteriorated severely. They understood that their basic survival tactics, taking cover in holes, behind walls, in trenches, no longer worked. There was no defense against airburst artillery except dispersal over large areas, which was tactically impractical in most combat situations. German artillery doctrine, developed over decades and refined through 2 world wars, emphasized using terrain and field fortifications to protect troops from artillery fire. This doctrine had been validated in World War I, where properly dug trenches and dugouts could protect soldiers even from sustained bombardment. The proximity fuse invalidated this entire doctrinal framework. Defensive positions became death traps rather than protection. German forces had no effective countermeasure. They could not jam the fuses. German electronic warfare capabilities were limited and focused on other targets. They could not shoot down the shells. Anti-aircraft guns were ineffective against artillery. They could not avoid the bombardments. Tactical withdrawal was often impossible due to operational requirements. They simply had to endure casualties at rates far exceeding normal artillery effectiveness. American artillery officers interviewed post-war confirmed the tactical impact. Lieutenant Colonel Harold Coyle, who commanded an artillery battalion during the Battle of the Bulge, stated in his memoir that proximity fuses increased the effectiveness of his battalion's fire by approximately 300%. His unit could achieve effects with one battery that would previously have required 3 batteries firing conventional ammunition. Becker compiled his findings into a comprehensive report submitted to Oberkommando der Wehrmacht on January 28, 1945. The report was approximately 40 pages, divided into technical analysis, production assessment, and strategic implications. The technical section detailed the proximity fuse's operation, component specifications, and manufacturing requirements. Becker concluded that Germany could not replicate the device with current industrial capacity. Even if resources were concentrated on attempting to develop a German proximity fuse, production would not begin before late 1946 at the earliest and would likely never reach meaningful scale. The production assessment section compared American manufacturing capacity to German capacity across multiple categories: electronics production, precision machining, aluminum production, vacuum tube manufacture, and overall industrial output. In every category, American capacity exceeded German capacity by factors ranging from 3 to 1 to 10 to 1 or greater. The strategic implications section was the most controversial. Becker wrote, and this is preserved in captured German documents now in the US National Archives, the VT proximity fuse represents not merely an advanced weapon system, but evidence of industrial capacity operating at unprecedented scale. The ability to manufacture 40,000 complex electronic devices daily while simultaneously producing overwhelming quantities of conventional war material indicates an economic foundation Germany cannot match. If American industry can mass-produce miniature radar sets as standard artillery ammunition while also producing aircraft, naval vessels, armored vehicles, and supplies sufficient to equip both American forces and Allied forces on multiple fronts, then Germany's material position is not unfavorable but mathematically untenable. Continued military operations under these conditions will produce casualties without strategic benefit. Becker recommended immediate armistice negotiations. He argued that further combat would only increase German casualties without affecting the war's eventual outcome, which industrial mathematics had already determined. The report was forwarded through channels to OKW leadership. According to post-war testimony from surviving German officers, the report reached several high-level commanders but was ultimately dismissed. One general, sources differ on whether this was Jodl or Keitel, reportedly characterized Becker's analysis as defeatist mathematics that ignored the German soldiers' fighting spirit. The report was marked "No action required" and filed. Becker received no official response. Through informal channels, he learned that his conclusions were considered damaging to morale and potentially treasonous. No disciplinary action was taken against him, but he received no further assignments requiring strategic assessment. The proximity fuse had been deployed first in anti-aircraft roles, not against ground targets. This represented a deliberate security decision by Allied leadership, and understanding this deployment pattern provides context for the weapon's eventual use during the Battle of the Bulge. The fuse was first used operationally in January 1943 aboard cruisers in the Pacific. The USS Helena fired the first proximity-fused anti-aircraft rounds in combat during operations near Guadalcanal. Results were immediately significant. Anti-aircraft gunnery in World War II was notoriously difficult. Hitting a fast-moving aircraft with conventional ammunition required precise fuse timing, accurate range estimation, and considerable luck. Hit rates for conventional anti-aircraft fire rarely exceeded 3 to 5%. Proximity fuses dramatically improved these figures. Post-war analysis by the U.S. Navy Bureau of Ordnance indicated that proximity fuses increased anti-aircraft effectiveness by approximately 500% compared to conventional timed fuses. A gun that required an average of 1,000 rounds to achieve one aircraft kill using conventional ammunition required only 200 rounds with proximity fuses. This improvement had immediate tactical effects. Japanese air attacks on U.S. Navy task forces became significantly more costly for the attackers. American ships that previously would have been damaged or sunk by sustained air attack could now defend themselves effectively. The proximity fuse became standard equipment for all U.S. Navy anti-aircraft guns by mid-1943. The weapon was kept strictly secret from ground combat to prevent enemy capture and reverse engineering. All unexploded proximity-fused shells that fell on land or water were to be recovered if possible. Navy ships were instructed to use proximity fuses only over water, where recovery by enemy forces would be unlikely. These security measures were maintained throughout 1943 and most of 1944. The British received proximity fuses through Lend-Lease arrangements and deployed them against V-1 flying bombs during the summer of 1944. The V-1 was a jet-powered cruise missile that Germany launched against England, primarily targeting London. British anti-aircraft defences, equipped with proximity-fused ammunition, achieved remarkable success rates against these weapons. Guns using conventional ammunition destroyed approximately 24% of V-1s that entered their engagement zones. Guns using proximity fuses destroyed approximately 79%. This dramatic improvement effectively neutralized the V-1 threat once sufficient proximity-fused ammunition became available. The decision to deploy proximity fuses in ground combat during the Battle of the Bulge represented a significant policy change. Previously, the fuses had been restricted to anti-aircraft use to minimize capture risk. German forces, however, launched their Ardennes offensive on December 16, 1944, achieving tactical surprise and creating a crisis situation for Allied forces. American artillery units defending Bastogne and other critical positions received authorization to use proximity fuses against German ground forces. This was the first large-scale use of the weapon in ground combat. The tactical impact was immediate and severe for German attackers. American artillery doctrine emphasized rapid, accurate fire. Forward observers directed fire from multiple batteries onto target areas. With conventional fuses, artillery fire against troops in field fortifications required sustained bombardment to achieve significant casualties. With proximity fuses, a single volley could devastate an area previously considered protected by trenches and foxholes. Colonel Harold Coyle's battalion, mentioned earlier, fired approximately 2,400 rounds with proximity fuses during the Battle of the Bulge. Post-battle damage assessment indicated these rounds produced casualty effects equivalent to approximately 7,200 rounds of conventional ammunition, based on examination of German casualty reports from units that had been engaged. German forces adapted as best they could. Some units attempted extreme dispersal, but this reduced their tactical effectiveness and made them vulnerable to other forms of attack. Other units attempted to move only at night or during poor visibility, but American artillery could fire effectively regardless of visibility. They relied on forward observers and map coordinates, not direct observation of targets. Some units attempted to advance rapidly through artillery fire, accepting heavy casualties, but this exhausted troops and disrupted unit cohesion. No effective countermeasure existed. German forces simply had to accept that American artillery was now 3 to 5 times more effective than conventional artillery and plan operations accordingly. This typically meant that operations that would previously have been considered viable now required unacceptable casualty risk. After Germany's surrender, Allied authorities conducted comprehensive assessments of German military capabilities and industrial capacity. These assessments, combined with now declassified Allied production data, confirmed and exceeded Becker's wartime estimates. The final production total for VT proximity fuses was 22,058,000 units according to U.S. Army Ordnance Department records. These fuses were manufactured by multiple contractors: Western Electric, approximately 8.5 million units, Eastman Kodak, approximately 4.2 million units, Crosley Corporation, approximately 3.8 million units, Raytheon, approximately 2.1 million units. Other contractors, approximately 3.5 million units production, peaked in March 1945 at approximately 52,000 units per day. Total program cost exceeded $1.1 billion in 1940s dollars, making it comparable in expenditure to the Manhattan Project that developed atomic weapons. But the proximity fuse was deployed and used on a scale the atomic bomb was not. The two atomic weapons dropped on Japan, while historically significant, directly affected two cities. The 22 million proximity fuses affected combat operations across both European and Pacific theaters for over 2 years. British analysis, conducted by operational research teams that had studied weapons effectiveness throughout the war, concluded that proximity fuses provided the following improvements over conventional fuses. Anti-aircraft effectiveness, 500% improvement. Anti-personnel artillery, 300% improvement. Cost effectiveness. Despite being more expensive per unit, the reduced ammunition expenditure required made them more economical overall. German post-war analysis, conducted by captured engineers and scientists working for Allied technical intelligence, confirmed that Germany could not have developed comparable technology with wartime resources. The miniaturization requirements, ruggedization challenges, and mass production demands exceeded German industrial capabilities even before the war began seriously degrading German manufacturing capacity. The proximity fuse story illustrates broader patterns in World War II that extended beyond any single weapon system. Germany entered the war with superior tactical doctrine, well-trained forces, and sophisticated weapons technology in many areas. Germany lost the war because of industrial capacity disparities that no amount of tactical skill could overcome. Several statistics illustrate this disparity. These figures are from official records compiled by government statistical agencies. Aircraft production, total war period: United States, 324,550 aircraft; Germany, 119,307 aircraft; Soviet Union, 157,261 aircraft; Britain, 131,049 aircraft; Japan, 76,320 aircraft. The United States alone produced more aircraft than Germany and Japan combined. American aircraft were on average more complex, 4-engine heavy bombers versus primarily single or twin-engine aircraft for Germany and Japan, meaning the industrial capacity gap was even wider than raw numbers suggest. Tank production showed similar patterns. United States, 88,410 tanks and self-propelled guns. Soviet Union, 105,251 tanks and self-propelled guns. Germany, 67,429 tanks and self-propelled guns. Britain, 31,896 tanks and self-propelled guns. Again, the combined Allied production exceeded Axis production by factors of 4 or 5 to 1. And this production occurred while Allied industries simultaneously manufactured aircraft, ships, trucks and ammunition in quantities Germany could not approach. Perhaps most telling was truck production. Military logistics in World War II depended heavily on motor transport. The US produced approximately 2.4 million military trucks. Germany produced roughly 350,000. This 7-to-1 advantage in logistics vehicles translated directly into operational tempo. American forces could move, supply and sustain operations at rates German forces could not match. The proximity fuse was simply one example of how this industrial disparity manifested in specific weapons systems. American industry could afford to design and manufacture sophisticated electronics for one-time use munitions. German industry struggled to produce sufficient quantities of basic ammunition with simple mechanical fuses. Becker's analysis in January 1945 accurately identified these realities. His report was dismissed not because it was factually wrong, but because accepting its conclusions would have required acknowledging that Germany's strategic position was hopeless. The Nazi regime, built on premises of German superiority, could not accept evidence of systematic material inferiority, regardless of how compelling that evidence was. This pattern repeated across German military and civilian leadership. Accurate assessments were produced by competent professionals, intelligence officers, engineers, economists, field commanders, and were rejected when they contradicted ideological premises. The cost of this willful blindness was measured in hundreds of thousands of additional casualties sustained fighting a war whose outcome had been determined by industrial mathematics. The proximity fuse changed warfare permanently. Modern artillery remains heavily dependent on electronically fused munitions. The principle Becker examined in January 1945, letting the munition determine its own optimal detonation point, is now standard across multiple weapon systems. But the broader lesson extends beyond military technology. When evidence contradicts ideology, when accurate assessment threatens established belief, organizations face a choice: adapt to reality or maintain comfortable myths. Germany chose myths. The choice proved fatal.